There's a photograph that shouldn't exist. The James Webb Space Telescope just captured an image so deep into space, so far back in time, that what it revealed has left astronomers questioning everything we thought we knew about the universe. We're talking about galaxies that formed when they simply couldn't have formed, stars that existed before they had time to exist, and structures so mature, so organized that their presence in the early universe makes no sense according to our current understanding of physics. What Webb found doesn't just challenge our theories, it forces us to rewrite the entire story of how the cosmos came to be. So what exactly did this telescope see that has the scientific community in such turmoil? What cosmic rules did these ancient galaxies break? And why does this single photograph have the power to change everything we believe about the Big Bang, dark matter, and the very fabric of reality itself? To understand why this discovery is so earth-shattering, we need to take a step back and look at what we expected to find out there in the first place. For decades, the Hubble Space Telescope was our eye in the sky. Launched in 1990, Hubble revolutionized astronomy by giving us a clear view of the universe from above Earth's blurring atmosphere. It showed us distant galaxies, nebulae, and cosmic events that captured our imagination. Hubble gave us those iconic images of deep space that decorated classrooms and inspired a generation of scientists. The telescope's deep field images, where it stared at tiny patches of seemingly empty sky for days at a time, revealed thousands of galaxies in every direction. It was proof that the universe is far more crowded and ancient than anyone had previously imagined. The Hubble Deep Field, captured in 1995, was a watershed moment in astronomy. Scientists pointed the telescope at a seemingly empty patch of sky, no bigger than a grain of sand held at arm's length, and let it collect light for 10 consecutive days. What emerged from that long exposure was breathtaking. Over 3,000 galaxies appeared in that tiny speck of sky. Galaxies of every shape and color, from nearby spirals to distant red smudges representing some of the most ancient structures in the cosmos. If every part of the sky contained this many galaxies, astronomers realized, then the observable universe must contain hundreds of billions of galaxies, each with hundreds of billions of stars. The numbers were staggering and humbling at the same time, but there was always a limit to what Hubble could see. It worked mainly with visible light and a bit of ultraviolet and near-infrared, which meant the most ancient and distant objects in the universe remained hidden behind a cosmic veil. Think of it like trying to see through fog with your regular vision. You can make out shapes nearby, but anything really far away just fades into gray nothingness. Hubble could see galaxies that formed a few billion years after the Big Bang, but the very first galaxies, the ones that lit up the universe after the Dark Ages, remained frustratingly out of reach. Astronomers knew these ancient galaxies had to be out there, but Hubble simply wasn't equipped to find them. The problem is that light from the most distant galaxies has been traveling toward us for billions of years, and during that journey, the universe itself has been expanding. This expansion stretches the light waves, shifting them from visible wavelengths into the infrared spectrum. It's called redshift, and it's the key to understanding why we needed something more powerful than Hubble. When astronomers talk about redshift, they're describing how light gets stretched as space expands. Imagine drawing dots on a balloon and then inflating it. As the balloon expands, the dots move farther apart. Light waves behave similarly as the universe expands. Their wavelengths get longer, shifting toward the red end of the spectrum, and eventually into infrared wavelengths that our eyes can't see. The concept of redshift was first discovered by Edwin Hubble himself in the 1920s. He observed that galaxies were moving away from us, and the farther away they were, the faster they were receding. This observation led to the understanding that the universe is expanding. The redshift of a galaxy's light tells us how much the universe has expanded since that light was emitted. A galaxy with a redshift of 1 has light that's been stretched by a factor of 2, meaning the universe has doubled in size since the light left that galaxy. A galaxy with a redshift of 10, which represents the very early universe, has light stretched by a factor of 11. The farther away something is, the more its light gets stretched, and eventually it shifts so far into the infrared that Hubble simply can't detect it anymore. Hubble's instruments were optimized for visible and ultraviolet light, with only limited infrared capability. The telescope could see galaxies with redshifts, up to about 6 or 7, corresponding to galaxies that formed about 1 billion years after the Big Bang. But galaxies that formed in the first few 100 million years with redshifts of 10, 15, or even higher remained invisible. Their light had shifted completely out of Hubble's detection range. This is where James Webb comes in. The James Webb Space Telescope was specifically designed to see in infrared. Its massive mirror, measuring 6.5 meters across and almost 3 times the area of Hubble's, collects faint infrared light from the most distant reaches of space. This isn't just an upgrade, it's a completely different way of looking at the universe. Webb's mirror is made up of 18 hexagonal segments, each coated with a microscopically thin layer of gold. Gold is an excellent reflector of infrared light, making it the perfect choice for this mission. Each mirror segment weighs about 20 kilograms and is made of beryllium, a metal that's both lightweight and incredibly stable at the extremely cold temperatures where Webb operates. The mirror segments can be individually adjusted with incredible precision, allowing the telescope to focus perfectly despite the extreme cold of space. Each segment has 7 actuators on the back that can move it with precision measured in nanometers, billionths of a meter. This level of control is necessary because even tiny imperfections in the mirror's shape can blur the images. During the months after launch, engineers carefully aligned all 18 segments so they worked together as a single perfect mirror. The alignment process was so successful that Webb's images are even sharper than scientists had hoped. And speaking of cold, Webb operates at incredibly low temperatures, around -233 degrees Celsius. This is necessary because infrared detectors need to be cold to avoid being overwhelmed by their own heat signature. Everything that has temperature emits infrared radiation. At room temperature, the telescope itself would glow brightly in infrared, drowning out the faint signals from distant galaxies. To achieve these frigid temperatures, Webb sits at a point in space called the second Lagrange point, or L2, about 1.5 million kilometers from Earth, where a massive sunshield the size of a tennis court protects it from the sun's heat. The sunshield is one of Webb's most critical components. It's made of 5 layers of a material called capton, each layer thinner than a human hair. The layers are separated by gaps that create insulating vacuum spaces. The sun-facing side of the shield can reach temperatures of 85 degrees Celsius, hot enough to boil water, while the telescope side stays at -233 degrees Celsius. That's a temperature difference of over 300 degrees across the width of the sunshield. This remarkable engineering keeps the telescope cold enough to detect the faint infrared glow of the most distant galaxies in the universe. Webb can peer through cosmic dust clouds that block visible light. Dust is common in space, made of tiny grains of carbon, silicon, and other elements. These dust grains scatter and absorb visible light but allow infrared light to pass through. This means Webb can see into regions that are completely opaque to Hubble, like the dense clouds where new stars are forming or the dusty centers of distant galaxies. It can detect heat signatures from objects that are too cold or too far away to shine brightly in visible wavelengths. Most importantly, it can see the light from galaxies that formed just a few 100 million years after the Big Bang, galaxies that have been invisible to us until now. The telescope's instruments can break down the light from distant objects into spectra, revealing their chemical composition, temperature, motion, and distance. This spectroscopic capability is crucial for confirming just how far away these ancient galaxies really are. Webb carries 4 main scientific instruments. The near-infrared camera, or NER-CAM, is the telescope's primary imager. It's what captured the stunning deep-field images we're discussing. The near-infrared spectrograph, NIR-SPEC, can simultaneously capture spectra from hundreds of objects, allowing astronomers to efficiently study large numbers of galaxies. The mid-infrared instrument, MIRI, extends observations to longer wavelengths and includes both a camera and a spectrograph. And the fine guidance sensor and near-infrared imager and slitless spectrograph, mercifully abbreviated as FGS-NIRIS, helps keep the telescope precisely pointed and provides additional imaging and spectroscopy capabilities. When Webb turned its gaze toward a patch of sky and captured what scientists call an ultra-deep field image, it was like switching from a blurry old television to ultra-high definition. The image revealed details that had never been seen before. Suddenly, there were thousands of galaxies visible in a single frame. Spirals, ellipticals, irregular blobs of stars, all scattered across the cosmic landscape. Some galaxies appeared as they were just a few billion years ago, relatively nearby in cosmic terms. Others were so distant that their light had been traveling toward us for over 13 billion years. The dynamic range of the image was extraordinary, capturing both bright nearby galaxies and faint distant ones in the same exposure. But it wasn't just the number of galaxies that stunned researchers, it was what those galaxies looked like and when they existed. Mixed in with the expected population of faint, small, distant galaxies were objects that seemed completely out of place. Large, bright, structured galaxies appearing at distances corresponding to just 300 to 700 million years after the Big Bang. These weren't tiny smudges of light, they were substantial objects with clear structure and, in some cases, masses, comparable to major galaxies in the nearby universe. At first, some scientists thought these might be errors in the data or unusual nearby objects masquerading as distant galaxies. Maybe they were cool dwarf stars in our own galaxy, whose infrared emission happened to mimic that of distant galaxies. Maybe there was some instrumental artifact creating false detections. Maybe the redshift measurements were wrong. Astronomers are trained to be skeptical, especially when observations challenge fundamental theories. The first response to unexpected results is always to check for errors. But as more observations came in and the measurements were verified using multiple independent methods, it became clear that these galaxies were real and they were exactly where they appeared to be, in the very early universe. The confirmation came from spectroscopy. By spreading out the light from these galaxies into a spectrum, astronomers could identify specific emission and absorption lines from hydrogen, oxygen, and other elements. These spectral features appear at precise wavelengths in a laboratory. When observed in a distant galaxy, they're shifted to longer wavelengths by a precise amount that depends on the galaxy's distance. Multiple spectral lines, all shifted by the same factor, provided ironclad confirmation that these galaxies really were at the extreme distances indicated by their brightness and colors. There was no escaping the conclusion: these massive, mature galaxies really did exist just a few 100 million years after the Big Bang. According to our current understanding of cosmology, the universe began with the Big Bang roughly 13.8 billion years ago. This date comes from multiple independent measurements, including the rate of cosmic expansion, the temperature of the cosmic microwave background radiation, and the ages of the oldest stars. Different methods all converge on the same age, giving us confidence that the number is correct to within about 1%. In those first moments after the Big Bang, everything was incredibly hot and dense. The entire universe was compressed into a space smaller than an atom, with temperatures exceeding trillions of degrees. At these extreme conditions, matter as we know it couldn't exist. Instead, there was a soup of fundamental particles and energy. As the universe expanded and cooled over the first few minutes, protons and neutrons formed and began to combine into the nuclei of the lightest elements. This process, called Big Bang nucleosynthesis, produced mostly hydrogen, about 75% by mass, some helium, about 25%, and tiny traces of lithium and beryllium. The proportions of these elements are determined by the physics of nuclear reactions and the density and temperature of the universe at the time. Remarkably, when we measure the abundance of these elements in the oldest stars and gas clouds today, we find exactly the proportions predicted by Big Bang nucleosynthesis. This agreement between prediction and observation is one of the strongest pieces of evidence for the Big Bang theory. For several 100,000 years after that, the universe was still too hot for atoms to form. Free electrons scattered light in all directions, making the universe opaque, like being inside a glowing fog. Photons couldn't travel far before bouncing off an electron and changing direction. This meant that the universe was essentially opaque to light. If you could have been there with your eyes, you wouldn't have been able to see anything beyond the glowing plasma immediately surrounding you. But eventually, around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei and form complete atoms. This moment is called recombination, and it's when the universe became transparent for the first time. The light that was released at recombination is still traveling through space today. We detect it as the cosmic microwave background radiation, a faint glow coming from every direction in the sky. This radiation is one of the strongest pieces of evidence for the Big Bang theory. Its temperature and patterns match predictions perfectly and tell us about the conditions in the early universe. The CMB has a nearly perfect thermal spectrum corresponding to a temperature of 2.7 Kelvin, just a few degrees above absolute zero. This is exactly what you'd expect from a hot Big Bang that has been cooling for nearly 14 billion years as the universe expanded. Tiny variations in the temperature of this radiation, just a few millionths of a degree, represent regions that were slightly denser than average. These dense regions would eventually collapse under their own gravity to form the first structures in the universe. The patterns in the CMB fluctuations tell us about the physics of the very early universe. The size of the largest fluctuations, for example, depends on how fast sound waves could travel through the primordial plasma. By measuring these patterns precisely, cosmologists can determine fundamental properties of the universe, like its age, composition, and geometry. The CMB data from satellites like WMAP and Planck have revolutionized cosmology, turning it from a field dominated by uncertain estimates into a precision science. After recombination came the Dark Ages, a period lasting several 100 million years when the universe was filled with neutral hydrogen gas but contained no sources of light. No stars had formed. Yet, the universe was literally dark except for the fading glow of the cosmic microwave background, which by this time had cooled and shifted into infrared wavelengths. The term Dark Ages is quite literal. If you could have observed the universe during this period, you would have seen only blackness. The CMB had faded to invisibility, shifted far into the infrared, and no stars or galaxies had formed yet to light things up. During the Dark Ages, gravity was slowly pulling gas together into clumps. Dark matter, which doesn't interact with light but exerts gravitational force, had already begun forming a cosmic web of filaments and nodes. The distribution of dark matter wasn't completely uniform. It had tiny density variations, inherited from quantum fluctuations in the extremely early universe that had been amplified by a process called cosmic inflation. Regions that were slightly denser than average had slightly stronger gravity, so they attracted more matter. Over time, the dense regions became denser and the sparse regions became sparser. This process, called gravitational instability, is how structure grows in the universe. Regular matter, the hydrogen and helium gas, was falling into these gravitational wells. The gas didn't fall in smoothly, though. As it fell toward the dense regions, it heated up from compression. The gas atoms collided with each other more frequently, and their kinetic energy increased. In order to collapse further, the gas needed to cool down and radiate away this heat. In the modern universe, gas cools through various mechanisms. Metal atoms and molecules are very efficient at radiating energy. But in the pristine gas of the early universe, there were no metals yet. The only cooling mechanism was hydrogen emission, which is much less efficient. This meant that gas could only collapse where the density was high enough and the temperature was low enough, setting a minimum mass for the first structures to form. Eventually, after a few 100 million years, the gas clumps became dense enough and hot enough to ignite nuclear fusion. Hydrogen atoms were slammed together with such force that they fused into helium, releasing enormous amounts of energy. The first stars were born. This moment, when the first stars lit up and ended the cosmic dark ages, is called the epoch of Ryanization. It's one of the key eras in cosmic history that Webb was designed to study. These early stars were different from stars today. They formed from pristine gas that contained only hydrogen and helium, no heavier elements at all. Computer simulations suggest these first stars were massive, perhaps 50 to 100 times the mass of our sun, maybe even larger. Without metals to help the gas cool, only very massive clumps could collapse. These massive stars burned incredibly hot and bright, with surface temperatures exceeding 50,000 degrees. For comparison, the surface of our sun is about 5,500 degrees. These first stars would have been brilliant blue-white beacons, far more luminous than typical stars today. A single one of these stars could have shone with the light of 1,000,000 suns. These massive stars lived fast and died young. Within just a few million years, they had burned through their hydrogen fuel and begun fusing heavier elements in their cores. The fusion process in stars works like a cosmic alchemy. First, hydrogen fuses into helium. When the hydrogen in the core is exhausted, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. Then carbon fuses into neon, neon into magnesium, and so on up the periodic table. Each stage releases less energy than the previous one and lasts for a shorter time. The final stage, silicon fusion producing iron, lasts only about a day in a massive star. Carbon, oxygen, neon, silicon, and eventually iron were forged in the nuclear furnaces at the hearts of these stars. Elements heavier than iron, like copper, silver, and gold, can't be produced by normal fusion because fusing iron consumes energy rather than releasing it. These heavier elements are created in the extreme conditions of supernova explosions through a process called rapid neutron capture. When they finally ran out of fuel, they exploded as supernovae, some of the most energetic events in the universe. A supernova explosion releases as much energy in a few weeks as our sun will produce over its entire lifetime. These explosions scattered the newly created heavy elements into the surrounding gas. For the first time, the universe contained metals, the astronomical term for any element heavier than helium. The gas now had a fundamentally different composition than it did before. Even a tiny amount of metals changed how the gas behaved. Metals are very efficient at radiating energy, which meant that the enriched gas could cool much faster. This allowed smaller clumps to collapse and form stars. The second generation of stars could therefore include lower mass stars like our sun, stars that would live for billions of years rather than just millions. The enriched gas could now form a new generation of stars, stars that contained small amounts of these heavy elements. Over time, more and more stars formed, died, and enriched the universe with metals. Each generation added to the cosmic stockpile. This process of stellar birth, death, and enrichment is fundamental to the evolution of the universe. Heavy elements like carbon, nitrogen, and oxygen are essential for planets and life. Carbon is the backbone of organic chemistry. Oxygen is necessary for water and for the metabolic processes of life. Iron is crucial for geology and biology. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged inside a star that lived and died billions of years ago. We are quite literally made of stardust. Small galaxies began to form as groups of stars bound together by gravity. These proto-galaxies were small and irregular, containing perhaps a few million stars. They were nothing like the grand spiral and elliptical galaxies we see in the nearby universe. They were messy, clumpy collections of stars with no organized structure. Their formation was chaotic, driven by the collapse of gas in the densest regions of the dark matter web. Over time, they collided and merged with one another. Each merger triggered new waves of star formation as gas clouds collided and compressed. The compression heated the gas, but it also increased its density, and once dense enough, regions would collapse to form new stars. Gradually, over billions of years, these small building blocks assembled into the large galaxies we see today. This hierarchical model of galaxy formation, where small structures merge to form larger ones, is a cornerstone of modern cosmology. It's supported by computer simulations and observations of galaxies at different cosmic epochs. We can see this process happening in the universe today. The Milky Way is currently absorbing several small satellite galaxies. The Sagittarius dwarf elliptical galaxy, for example, is being torn apart by the Milky Way's gravity. Its stars are being added to our galaxy's halo. In about 4 billion years, the Milky Way will collide with the much larger Andromeda galaxy, and the two will merge to form a giant elliptical galaxy. The universe needed time to build up from simple to complex, from small to large, from chaotic to organized. The standard model of cosmology, called lambda CDM, describes this process in detail. Lambda refers to dark energy, the mysterious force causing the universe's expansion to accelerate. It's represented by the Greek letter lambda, which Einstein originally used to denote the cosmological constant in his equations. CDM stands for cold dark matter, the invisible substance that provides the gravitational scaffolding for galaxy formation. According to lambda CDM, structure formation happens gradually. The tiny density fluctuations present at recombination grow slowly under gravity. Dark matter clumps first because it's not affected by radiation pressure. Regular matter then falls into the dark matter halos and begins forming stars. This model makes specific predictions about when different types of structures should appear. Small galaxies should form first within a few 100 million years after the Big Bang. These should be low-mass objects, perhaps 10 million to 100 million solar masses, much smaller than the Milky Way's trillion solar masses. Larger galaxies should take longer, perhaps 1 billion years or more. They form through the merger of smaller galaxies, a process that can't happen instantaneously. The most massive galaxy clusters containing thousands of galaxies should only appear several billion years after the Big Bang. These clusters form at the nodes of the cosmic web, where multiple filaments of dark matter intersect. It takes time for enough galaxies to fall into these regions and for the cluster to virialize to reach a stable configuration. The model also predicts what these early galaxies should look like. They should be small, typically containing a few million to a few tens of millions of stars. They should be irregular and clumpy in shape, not yet having had time to settle into organized structures like spiral disks. Their star formation should be chaotic, happening in intense bursts triggered by mergers and gas infall. And they should have low levels of heavy elements, since only a few generations of stars would have lived and died by that point. The metal content should be perhaps 1/100th or 1,000th of what we see in modern galaxies like the Milky Way. That's the story we've been telling based on observations from Hubble and ground-based telescopes, and it made sense. Everything fit together in a neat timeline that matched our theoretical models. Hubble's observations of distant galaxies, combined with studies of the cosmic microwave background by satellites like WMAP and Planck, all painted a consistent picture. The universe began in a hot, dense state, expanded and cooled, formed the first stars after a few 100 million years, and gradually assembled those stars into ever larger galaxies over billions of years. The Lambda CDM model successfully explained the large-scale structure of the universe, the properties of the cosmic microwave background, the abundance of light elements, the expansion history, and the distribution and properties of galaxies at different epochs. It was a triumph of modern cosmology. But then Webb looked deeper than we've ever looked before, and it saw something that didn't fit. In regions of space corresponding to just 300 to 500 million years after the Big Bang, Webb found galaxies that looked nothing like the small, messy, immature structures we expected. Instead, it found massive, well-organized galaxies with clear spiral structures, abundant heavy elements, and properties that suggest they had already undergone billions of years of evolution, except they couldn't have. There simply wasn't enough time. The discrepancy wasn't subtle. These galaxies were off by factors of 5 or 10 in their properties compared to predictions. That's not a small error that can be explained by measurement uncertainties. It's a fundamental mismatch. Imagine you're watching a time-lapse video of a forest growing. You see seeds sprout, saplings emerge, and over many years, those saplings slowly grow into mature trees. The process is gradual and predictable. Each stage takes a certain amount of time. Seedlings need years to become saplings. Saplings need decades to become mature trees. The tallest trees in the forest are also the oldest, having grown for centuries. Now imagine you rewind that video to the very beginning, just minutes after the seeds were planted, and suddenly you see fully grown oak trees towering above the ground, their trunks thick, their branches spreading wide, their roots deep in the soil. That's essentially what Webb has shown us. The cosmic forest was supposed to be filled with baby trees at this early stage, seedlings and saplings just beginning to grow. But instead, we're seeing ancient giants, trees that look like they've been growing for centuries. Let's talk about the specifics of what makes these galaxies so impossible. First, there's the mass problem. Some of the galaxies Webb detected in the early universe have masses comparable to the Milky Way, or even larger. To put that in perspective, the Milky Way contains somewhere between 200 and 400 billion stars and has been accumulating mass for over 13 billion years. Our galaxy has grown through countless mergers with smaller galaxies and continuous star formation throughout its history. The Milky Way is still forming about 1 or 2 new stars every year, and it's still growing by absorbing smaller satellite galaxies. It's a mature, fully developed galaxy that represents the endpoint of billions of years of evolution. These early galaxies somehow achieved similar mass in just a few 100 million years. That's like building a skyscraper in the time it should take to lay the foundation and pour the concrete for the ground floor. Actually, it's even more extreme than that. It's like showing up to a construction site on day one and finding a completed building, fully furnished and ready for occupancy. The mass has to come from somewhere. In the case of galaxies, it comes from gas that collapses and turns into stars. But there are limits to how fast this can happen. The mass of a galaxy is determined by analyzing its light. Astronomers look at how bright the galaxy is and what colors it emits. Different types of stars produce different amounts and colors of light. Young, hot stars are very bright and blue. They're massive stars that burn their fuel quickly, living only a few million years. These stars dominate the light from young, actively star-forming galaxies. Older, cooler stars are dimmer and red. They're lower-mass stars that burn their fuel slowly, living for billions of years. These stars dominate the light from older, quiescent galaxies where star formation has stopped. By analyzing the spectrum of light from a galaxy, scientists can estimate how many stars it contains and what their ages are. The technique is called stellar population synthesis. Astronomers create models of how galaxies should look at different ages and with different star formation histories. They then compare the observed spectrum to these models to determine which one provides the best match. From this, they can infer the total stellar mass, the average age of the stars, the rate of star formation, and the metal content. When this analysis was applied to some of Webb's early galaxies, the results were shocking. These galaxies contained stellar populations consistent with tens of billions or even hundreds of billions of stars. The sheer amount of mass in stars was staggering for objects that existed so early. In our standard model of galaxy formation, called the lambda CDM model, galaxies grow gradually. Small proto-galaxies form first, containing maybe a few million stars. These proto-galaxies are built when the very first stars group together under gravity. Their masses are typically in the range of 1 million to 10 million times the mass of the Sun. Over time, they collide and merge with other small galaxies. Gravity brings them together. When galaxies move, through the cosmic web, they encounter each other. If they're moving slowly enough, their mutual gravity will cause them to fall toward each other and eventually collide. When two small galaxies collide, their gas clouds smash into each other, heating up and triggering intense bursts of star formation. The collision compresses the gas, increasing its density. Dense gas cools efficiently and collapses to form stars. A merger between two gas-rich galaxies can turn a large fraction of their gas into stars within a few 100 million years, producing a starburst galaxy. These starburst galaxies can form stars at rates hundreds of times higher than the Milky Way's current rate. Each merger adds a mass and triggers new waves of star formation. This process continues for billions of years, slowly building up the massive galaxies we see in the nearby universe. Today, our own Milky Way is still growing through this process. We're currently in the process of absorbing several small satellite galaxies. The Sagittarius dwarf elliptical galaxy is the closest of these, currently about 70,000 light-years from Earth on the far side of the galaxy. It contains about 1 billion stars and is being torn apart by the Milky Way's tidal forces. Its stars and gas are being incorporated into our galaxy's halo. Over the next few billion years, it will be completely absorbed. The Large and Small Magellanic Clouds, two dwarf galaxies visible from the southern hemisphere, are also falling toward the Milky Way and will eventually merge with it. And in a few billion years will collide and merge with the Andromeda Galaxy, which is about the same size as the Milky Way. That merger will be spectacular, though no individual stars are likely to collide. The galaxies will pass through each other, then fall back together, and after a few passes will merge to form a single giant elliptical galaxy that astronomers have nicknamed Milkomeda. According to this model, the early universe should be populated with these small building blocks, not finished structures. When we look at regions of space corresponding to a few 100 million years after the Big Bang, we should see lots of small, faint proto-galaxies. Some of them might be in the process of merging, creating slightly larger galaxies. But we shouldn't see huge mature galaxies because they haven't had time to grow through enough mergers yet. The timeline simply doesn't allow for it. You need billions of years and dozens or hundreds of mergers to build up a Milky's Way-sized galaxy from small proto-galactic building blocks. But Webb is showing us finished structures, galaxies with stellar populations that indicate they've already gone through multiple generations of star formation. We're talking about galaxies that should have taken 3 or 4 billion years to assemble, yet they're sitting there in the cosmic timeline at a point where they've only had 300 or 400 million years. The math doesn't work. The timeline is off by an order of magnitude. It's not just a small discrepancy that could be explained by refining our models. It's a fundamental mismatch between prediction and observation. When theory and observation disagree this strongly, something has to give. Either the observations are wrong, which seems unlikely given how carefully they've been checked, or the theory needs major revision. Some of these massive early galaxies have properties that are even more puzzling. A few appear to have already developed central bulges, the dense concentrations of stars found at the centers of many large galaxies. The Milky Way has a central bulge, a roughly spherical region about 6,000 light-years in radius that contains about 10 billion stars. The bulge is distinct from the disk, which is flat and contains spiral arms. In the nearby universe, bulges are thought to form through a combination of galaxy mergers and the growth of central supermassive black holes. Major mergers, where two galaxies of similar size collide, can destroy the disk and create a bulge. The violent gravitational interactions during the merger scramble the star's orbits, puffing up a spherical distribution. The formation of a bulge takes time because it requires many mergers and interactions. A galaxy needs to undergo at least one major merger, and probably several, to build up a substantial bulge. Finding galaxies with bulges at such early times suggests that the process of galaxy assembly was much more rapid than we thought. These galaxies must have already experienced multiple mergers by the time the universe was just a few 100 million years old. That's an extraordinarily compressed timeline. It implies that galaxy mergers were happening much more frequently in the early universe than our models predict. Then there's the metal problem. Remember how I mentioned that the first stars only had hydrogen and helium? Well, when those stars died, they released heavier elements. The explosions that marked the deaths of these stars were incredibly violent. Supernovae can briefly outshine entire galaxies, releasing as much energy in a few weeks as our sun will produce over its entire 10 billion year lifetime. A typical supernova releases about 10 to the power of 44 joules of energy. For comparison, our sun outputs about 3.8 times 10 to the power of 26 joules every second, so a supernova releases 100 times more energy than the sun will produce over its entire life. The blast waves from these explosions sweep up surrounding gas and enrich it with the elements forged inside the star. The explosion accelerates the gas to speeds of thousands of kilometers per second, creating a shock wave that plows through the interstellar medium. Behind the shock, the gas is hot and turbulent, mixing the metals from the supernova with the surrounding hydrogen and helium. Eventually, the enriched gas cools and can collapse to form new stars. Carbon, oxygen, neon, magnesium, silicon, sulfur, iron, and dozens of other elements are scattered into space. Each supernova enriches roughly 1,000 to 10,000 solar masses of gas, depending on how much gas is in the surrounding region. The next generation of stars form from gas that had been enriched with these metals. These second-generation stars had different properties than the first generation. The presence of metals, even in tiny amounts, changed how the gas cooled and collapsed. Metals are very efficient at radiating energy. A metal atom can absorb a photon, become excited, and then re-emit the photon in a random direction. This process removes energy from the gas and allows it to cool. The more efficiently gas can cool, the smaller the clumps that can collapse to form stars. This is why second-generation stars could be much less massive than first-generation. Stars like our sun, which are much smaller and longer-lived than those first massive stars, could only form once the universe had been enriched with metals. The sun is a third-generation or later star formed from gas that had been enriched by multiple previous generations. Its metal content is about 2% by mass, meaning that 2 out of every 100 atoms in the sun are heavier than helium. This may not sound like much, but it's sufficient to allow small stars like the sun to form and to allow planets like Earth to form from the leftover material. Each subsequent generation added more metals. Over billions of years, the metal content of the universe has steadily increased. The average metal content of the universe has gone from essentially zero at the beginning to about 0.1% today, with higher concentrations in galaxies where most of the star formation has occurred. This process is slow because stars need time to live out their lives before they die and release their metals. Massive stars die quickly, within a few million years, but they're relatively rare. For every massive star that forms, hundreds or thousands of lower mass stars form. Lower mass stars like our Sun are much more common, but they take billions of years to complete their life cycles. The Sun, for example, is currently about 4.6 billion years old and is only halfway through its life. It will continue shining for another 5 billion years before it swells into a red giant and eventually becomes a white dwarf. Only then will it return its metals to the interstellar medium. However, the Sun will only return a small fraction of its mass. Most of the mass will remain locked up in the white dwarf remnant. This means that the buildup of metals in the universe is a gradual process that plays out over cosmic timescales. The average metallicity of galaxies increases slowly with time. In the very early universe, at the time of the first galaxies, metallicities should be very low, perhaps 1,000th or 1/10,000th of the Sun's metallicity. A billion years later, metallicities might have risen to 1/100th of solar. Today, after nearly 14 billion years of evolution, typical galaxies have metallicities close to or even higher than solar. The Milky Way's interstellar gas, for example, has roughly solar metallicity in the solar neighborhood, but lower metallicities in the outer disk and halo. When astronomers analyzed the light from some of these early Webb galaxies, they found metal abundances that were surprisingly high. The technique used is called spectroscopy. By spreading out the light from a galaxy into a rainbow of colors, astronomers can identify dark lines where specific elements have absorbed light at characteristic wavelengths. Each element creates a unique pattern of lines, like a fingerprint. Hydrogen creates one pattern, with prominent lines at 663 nanometers in the red part of the spectrum and 486 nanometers in the blue. Oxygen creates another pattern, with strong lines in the ultraviolet and in the near infrared. Carbon creates another, nitrogen another, and so on. By measuring the strength of these absorption lines, scientists can determine how much of each element is present in the galaxy's stars and gas. Some galaxies showed levels of oxygen, carbon, and nitrogen that suggested multiple cycles of star formation and death had already occurred. The metal abundances were not just slightly higher than expected. In some cases, they were approaching levels seen in galaxies billions of years older. Some early galaxies had metallicities of 1/10th or even 1/3 solar, levels that shouldn't appear until several billion years after the Big Bang, according to standard models. This is mind-boggling because each cycle takes time. Stars must form, live out their lives, and die before they can enrich the next generation. To have gone through several cycles by the time the universe was only a few 100 million years old means that star formation must have been happening at an incredibly accelerated rate. Either that, or there was some mechanism in the early universe that produced metals faster than we currently understand. One theory suggests that the first stars were far more massive than we initially thought, perhaps hundreds of times the mass of our Sun. These supermassive stars, sometimes called population 3 stars because they'd represent the generation before population 2, the oldest stars we've found, and population 1, stars like the Sun, would have burned through their fuel in just a few million years and exploded in incredibly energetic supernovae called hypernovae, or pair instability supernovae. A pair instability supernova is a special type of explosion that can only occur in very massive stars. When the core of such a star gets hot enough, photons become energetic enough to spontaneously create electron-positron pairs. This creation process removes energy from the core, causing it to contract, which heats it up further, which creates more pairs, leading to a runaway instability. The star explodes completely, leaving no remnant. These explosions would have been far more powerful than typical supernovae, rapidly enriching the surrounding gas with huge amounts of metals. A single pair instability supernova could produce as much metal as dozens of regular supernovae. The explosion energy could be 10 times higher, and the mass of metals ejected could be 5 to 10 times higher. If the very first stars were massive enough to undergo pair instability supernova, they could have rapidly enriched their surroundings, allowing second-generation star formation to begin with higher metallicity than otherwise expected. But even this theory struggles to explain the sheer abundance of metals Webb is detecting. The number of these supermassive stars needed to produce the observed metal levels would have to be enormous. Every massive star in the early universe would need to have been in the pair instability mass range, which seems unlikely, and it's not clear that conditions in the early universe could have supported forming so many of them. Plus, these stars would have been so massive that some would have collapsed directly into black holes without exploding, taking their metals with them rather than scattering them into space. When a star is massive enough, more than about 140 solar masses in some models, it can undergo complete gravitational collapse. The core implosion creates a black hole, and the entire star falls into it without producing a supernova. No metals are ejected. This direct collapse channel would reduce the efficiency of metal production. It's like trying to explain how a brand new forest already has layers of decayed leaves and nutrient-rich soil when it's only been around for a few weeks. The metals we're seeing in these early galaxies represent the accumulated products of stellar evolution. They should take time to build up. Finding high metallicities so early in cosmic history implies that something was accelerating the process beyond what our standard models predict. Another possibility is that star formation itself was much more efficient in the early universe. In the modern universe, only a small fraction of gas in a galaxy actually turns into stars. Observations of nearby galaxies show that typically only about 1 to 5% of the gas-formed stars per freefall time, the time it would take for gas to collapse under its own gravity if nothing stopped it. Most of it remains as diffuse gas between the stars. This low efficiency is due to various feedback mechanisms that shut down star formation. When massive stars form, they emit powerful winds and intense ultraviolet radiation that heat up the surrounding gas and blow it away, preventing it from collapsing to form more stars. A massive star can produce stellar winds with speeds of thousands of kilometers per second, powerful enough to excavate huge bubbles in the interstellar medium. The radiation from hot stars ionizes the surrounding gas, creating regions where the pressure is much higher than in neutral gas. This pressure pushes the gas away from the star-forming region. When massive stars die as supernovae, their explosions create shock waves that also heat and disperse gas. A single supernova can inject enough energy to unbind thousands of solar masses of gas from a small galaxy. These feedback processes keep star formation in check. Without them, galaxies would turn all their gas into stars very quickly and then have no fuel for future star formation. Feedback regulates the process, ensuring that star formation happens gradually over billions of years. This is why big galaxies like the Milky Way are still forming stars today after 13 billion years. If star formation were 100% efficient, we would have used up all our gas long ago. But maybe in the early universe, these feedback mechanisms were less effective. Maybe the gas was able to cool and collapse more efficiently, allowing a much higher fraction of it to turn into stars. The early universe was denser than today because it hadn't expanded as much. Denser gas cools more efficiently because atoms collide more frequently. If the cooling time is shorter than the time it takes for feedback to drive the gas away, more gas can turn into stars before being disrupted. If star formation efficiency was 10 or 20 times higher in the early universe, it could help explain how galaxies grew so massive so quickly and why metal enrichment happened so rapidly. However, we don't have a good theoretical understanding of why star formation would have been so much more efficient back then. The physics of gas collapse and star formation should have been similar. Gravity pulls gas together, angular momentum makes it spin, and feedback from stars regulates the process. These physical principles don't change with time. So why would the early universe be different? Some researchers have proposed that the lower metallicity of early gas might have played a role. With fewer metals, cooling is less efficient in some temperature ranges, but that would make star formation less efficient, not more. It's a puzzle that remains to be solved, and then there's the structure problem. One of the most surprising aspects of the Webb observations is how organized some of these early galaxies appear. When astronomers zoom in on the high-resolution images, they can see the shapes of individual galaxies. Webb's angular resolution is about 0.1 arcseconds at 2 microns, which allows it to resolve features as small as a few hundred light-years across in these distant galaxies. Many of them are irregular and clumpy, which is what we expect. They look like messy collections of star-forming regions with no overall pattern. But a significant number show clear signs of structure. There are galaxies with disc-like shapes, flattened elliptical structures that suggest they're rotating. Some have hints of spiral arms, the beautiful winding patterns seen in nearby galaxies like Andromeda and the Milky Way. Spiral. Arms are regions of enhanced density that rotate around the galaxy, triggering star formation as gas clouds move through them. Some early galaxies show bright central concentrations surrounded by more diffuse outer regions, suggesting they've already developed a central bulge and a surrounding disk. In our current understanding, these features develop over time as galaxies settle down and organize themselves through gravitational interactions and rotational dynamics. When a galaxy first forms, it's typically irregular and chaotic. Gas clouds are moving in random directions, some falling in from outside, some being ejected by supernovae. Stars are forming wherever the gas is dense enough, creating bright clumps scattered throughout the galaxy. There's no overall pattern. The system hasn't had time to organize itself. But over time, as the galaxy undergoes mergers and interactions, it begins to spin. Conservation of angular momentum ensures that as gas falls into the galaxy's gravitational potential, it settles into a rotating disk. Gas that's moving perpendicular to the rotation axis falls to the midplane and joins the disk. Gas that's moving parallel to the rotation axis contributes to the disk's rotation. Over time, most of the gas ends up in a thin, rotating disk. The rotation causes the galaxy to flatten into a disk, with most of the stars and gas orbiting in the same plane. This is how spiral galaxies like the Milky Way form. The development of spiral arms requires even more time. Spiral arms are density waves that move through the galactic disk, regions where stars and gas bunch up due to gravitational interactions. They're not solid structures, more like traffic jams on a highway where cars bunch up and then spread out. Time runs. Stars and gas move into a spiral arm, slow down, spend some time there, and then move out the other side. The density wave itself rotates around the galaxy at a different speed than the stars and gas. The formation of these density waves requires a stable, settled disk that has been rotating for a long time. Theoretical models suggest that spiral structure takes at least 1 billion years to develop after the disk forms. In the nearby universe, we see spiral galaxies with beautifully defined arms, and we know these galaxies are billions of years old. The Andromeda Galaxy, our nearest large neighbor, is about 10 billion years old and has prominent spiral arms. The Whirlpool Galaxy, famous for its spectacular spiral structure, is also several billion years old. Finding galaxies with spiral structures at such early times is unexpected because the galaxies simply haven't had enough time to settle down and organize themselves. Young galaxies are supposed to be chaotic, irregular, and clumpy. They haven't had time to smooth out and form the elegant shapes we associate with mature galaxies. They should look messy, like a pile of building materials before a house is constructed, not like a finished building with organized rooms and a nice facade. Irregular galaxies in the nearby universe, like the Large Magellanic Cloud, give us an idea of what early galaxies should look like: clumpy, asymmetric, with no clear pattern. Yet here we are, looking at galaxies that existed when the universe was barely out of its infancy, and they're showing signs of maturity. Some have clear disks, some have spiral features, some have central bulges. These are all characteristics of galaxies that should be much older. It's as if the universe somehow skipped ahead in its development, jumping from childhood directly to middle age without going through adolescence. This challenges not just our models of galaxy formation, but also our understanding of how structure emerges in the universe. Structure formation is supposed to be a gradual, bottom-up process. Small structures form first and merge to create larger ones. But what Webb is showing us looks more like a top-down scenario, where large, complex structures appear early and then perhaps continue to grow. This doesn't fit with our theoretical framework at all. The Lambda CDM model is built on the idea of hierarchical structure formation. The cosmic microwave background shows that the universe started very smooth, with density variations of only 1 part in 100,000. These tiny variations grew under gravity, but the growth is slow at first. It takes hundreds of millions of years for the first small dark matter halos to collapse. Then these halos merge to form larger ones, which merge to form larger ones still. At each step, the timescale increases. If the early universe is producing mature, structured galaxies so quickly, it suggests that this hierarchical picture might be incomplete or wrong in some way. The discovery has sparked intense debate among cosmologists. Scientific conferences dedicated to discussing the Webb findings have been packed with researchers presenting competing theories and interpretations. The atmosphere at these meetings is electric, with scientists simultaneously excited by the discoveries and troubled by their implications. Some presentations defend the standard model, arguing that the observations can be explained with modifications to galaxy formation physics. Others propose more radical revisions to cosmology. The debates can get heated, but they're driven by a shared commitment to understanding the truth. Papers are being published at a furious rate, each offering a different perspective on what these observations mean. The rate of publication on this topic has increased dramatically since Webb's first deep fields were released. Hundreds of papers have been written analyzing different aspects of the early galaxy population, proposing theoretical explanations and debating the implications. The field is moving fast, with new ideas and results appearing weekly. It's an exciting time to be a cosmologist, even if the excitement is tinged with confusion and concern. Some researchers argue that our distance measurements might be off. Maybe these galaxies aren't as far away as we think. Maybe the redshift we're measuring is being influenced by some unknown factor. Redshift is determined by looking at specific features in a galaxy's spectrum, like the emission lines from hydrogen or oxygen. Hydrogen's Lyman alpha emission line, for example, appears at 121.6 nanometers in the laboratory. When we observe it in a distant galaxy, it's shifted to longer wavelengths. The amount of shift tells us how much the universe has expanded since the light was emitted, which in turn tells us the distance and age of the galaxy. It's a well-established technique that's been used for decades. The relationship between redshift and distance has been tested extensively using many different types of objects at different distances. But could there be something we're missing? Could there be additional sources of redshift that we haven't accounted for? The spectroscopic redshifts are very precise, typically uncertain by less than 1%. For the observed spectral lines to be misidentified would require an extraordinary coincidence. Multiple different emission lines would all have to be misidentified in exactly the same way to give the wrong redshift. This seems exceedingly unlikely. Some alternative theories propose that light could be redshifted by mechanisms other than cosmic expansion. For example, if light loses energy as it travels through space due to some unknown interaction, it could appear more redshifted than it should be. This idea is called tired light, and it's been around for nearly a century. It was first proposed in the 1930s as an alternative to the expanding universe model. But tired light theories have been thoroughly tested and rejected because they don't fit many other observations. They can't explain the cosmic microwave background, which is a direct prediction of the hot Big Bang model. They can't explain the time dilation observed in distant supernovae, where distant supernova light curves appear stretched out in time exactly as expected if the universe is expanding. They can't explain the evolution of galaxy properties with distance. For all these reasons, tired light has been abandoned by mainstream cosmology. Still, in the face of these puzzling Webb observations, some researchers are revisiting these old ideas. Perhaps there's a variant of tired light that could work, or perhaps there's some other unknown effect that modifies light from very distant sources. It's worth investigating, even if it seems unlikely. Science progresses by considering all possibilities, even unlikely ones. But so far, no alternative to the standard cosmological redshift interpretation has been able to explain the full suite of observations. If these galaxies are actually closer than we think, then they're also younger in cosmic time, which would give them more time to develop. A galaxy that appears to be 300 million years old might actually be 1 billion years old, which would make its mature properties less surprising. 1 billion years is enough time for significant galaxy evolution to occur. Multiple generations of stars could form and die, enriching the gas. Several mergers could happen, building up mass and structure. 1 billion years isn't enough time to fully explain the most extreme cases, but it would make the problem less severe. But this explanation has problems. The redshift measurements are based on solid physics, and multiple independent techniques all point to the same distances. Spectroscopy gives us precise redshift measurements from emission and absorption lines. The galaxy's brightness and colors are consistent with them being very distant based on our understanding of stellar populations. Nearby galaxies with similar colors are known to have certain ages and metallicities, and when we extrapolate to these distant objects, the properties match what we'd expect for very distant galaxies. And in some cases, the galaxies are gravitationally lensed by foreground galaxy clusters, which provides another independent confirmation of their distance. Gravitational lensing occurs when light from a distant object passes near a massive foreground object. The gravity of the foreground object bends the light, creating multiple images or arcs of the background object. The amount of bending depends on the masses of both objects and their relative distances. By studying the lensing geometry, astronomers can independently estimate the distance to the background galaxy. When this is done for some of the early Webb galaxies that happen to be lensed, the distances derived from lensing agree with the distances from redshift. It's unlikely that all of these methods are wrong in exactly the same way. Others suggest that our models of galaxy formation are simply incomplete. Perhaps there are processes we haven't accounted for that allow galaxies to form much faster than we thought possible. This is actually the most conservative explanation because it doesn't require throwing out our entire cosmological framework. The Big Bang model, dark matter, dark energy, all of that stays the same. It just means we need to tweak and refine our models of how gas turns into stars and how galaxies assemble. This is a more palatable explanation for many scientists, and it's the direction much of the current research is heading. Maybe the early universe was more efficient at converting gas into stars than we assumed. Modern galaxy formation simulations include many physical processes, from gravity and gas dynamics to star formation and feedback from supernovae and black holes. These simulations have hundreds of parameters, and many of those parameters are uncertain. The star formation efficiency, for example, is usually treated as a free parameter that's adjusted to match observations of nearby galaxies. If we adjust the star formation efficiency to be higher in the early universe, we might be able to produce galaxies that grow faster. Some recent simulations that use more aggressive star formation parameters are starting to produce early galaxies that look more like what Webb sees. By increasing star formation efficiency by a factor of 5 to 10 and reducing the strength of supernova feedback, these simulations can produce massive galaxies earlier than standard models. The resulting galaxies are more massive, have higher star formation rates, and can build up metals more quickly. However, these modifications are somewhat ad hoc. We're adjusting the parameters to match the observations, but we don't have a deep physical understanding of why the parameters should be different in the early universe. Maybe the conditions back then were so different from today that our extrapolations based on nearby galaxies just don't apply. The early universe was hotter, denser, and filled with more radiation. The cosmic microwave background radiation, while much cooler than at recombination, was still significantly hotter than today. At a redshift of 10, the CMB temperature would have been about 30 Kelvin instead of today's 3 Kelvin. This means that gas in the early universe had a higher minimum temperature, which affects how it cools and collapses. The gas that formed the first galaxies had never been processed through stars before. It was pristine, containing only hydrogen and helium from the Big Bang. Maybe these pristine conditions allowed stars to form in ways that don't happen in the modern universe. Without metals, the cooling mechanisms are different. Hydrogen molecules, formed when two hydrogen atoms bond together, provide most of the cooling in pristine gas. The formation and properties of these molecules depend on temperature, density, and the intensity of background radiation. Maybe the intense radiation from the first stars ionized the gas in ways that actually promoted further star formation rather than shutting it down. When the first stars formed, their intense ultraviolet radiation began to ionize the surrounding neutral hydrogen. This process is called reionization, and it transformed the universe from neutral to ionized over a period of several hundred million years. The ionized gas behaves differently than neutral gas. It's hotter and more difficult to compress. Conventional wisdom suggests that ionization should suppress star formation by heating the gas and preventing it from collapsing into small galaxies. But maybe in some circumstances, ionization could actually trigger star formation. If ionization creates regions of compressed gas at the boundaries between ionized and neutral regions, these compressed regions might collapse to form stars. These are possibilities that theorists are actively exploring. But there's a more radical possibility that some researchers are beginning to consider. What if the problem isn't with our galaxy formation models, but with our fundamental understanding of cosmology itself? What if the Big Bang model, as we currently understand it, needs a significant revision? This is a much scarier proposition because the Big Bang theory is supported by mountains of evidence. It explains the cosmic microwave background radiation, arguably the strongest single piece of evidence for the theory. The temperature and spectrum of this radiation match predictions perfectly. The CMB has a nearly perfect blackbody spectrum, exactly what you'd expect from a hot, dense early universe that has expanded and cooled. It explains the abundance of light elements in the universe. The proportions of hydrogen, helium, and lithium we observe match what we calculate should have been produced in the first few minutes after the Big Bang through Big Bang nucleosynthesis. The agreement is remarkable, with predicted and observed abundances matching to within a few percent. This is strong evidence that the early universe really did go through a hot, dense phase where nuclear reactions occurred. The Big Bang theory explains the expansion of the universe. We observe that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, called Hubble's law after Edwin Hubble, who first discovered it, is exactly what you'd expect if the universe began in a small, dense state and has been expanding ever since. The expansion is uniform in all directions, suggesting that it's space itself that's expanding, not galaxies moving through space. This cosmic expansion is a direct prediction of general relativity applied to a homogeneous universe. The theory explains why the universe looks the same in all directions on large scales, a property called isotropy. When we look at the distribution of galaxies on scales of hundreds of millions of light years, the universe appears uniform. There are no preferred directions or special locations. We appear to be in a typical place in a typical galaxy. This isotropy is a natural consequence of the Big Bang model, where the universe began uniformly and has expanded uniformly. It explains countless other observations, from the distribution of galaxies on cosmic scales to the properties of distant quasars. Quasars are the bright centers of galaxies powered by supermassive black holes. When we look at distant quasars, we see them as they were billions of years ago. Their properties are different from nearby quasars, showing that galaxies and black holes have evolved over time. The evolution follows patterns that match predictions from the Big Bang model. Overturning the Big Bang theory would require finding a new theory that explains all of those things just as well, while also accounting for these impossibly mature early galaxies. That's an incredibly tall order. Still, science has been overturned before. There was a time when everyone believed the Earth was the center of the universe. For over 1,000 years, the geocentric model of Ptolemy was accepted wisdom. The sun, moon, planets, and stars were thought to orbit the Earth on crystal spheres. Observations of planetary motions eventually forced us to accept that Earth orbits the sun, not the other way around. Copernicus proposed the heliocentric model in the 16th century, and Galileo's telescopic observations provided strong support. The discovery that Jupiter has moons orbiting it, for example, proved that not everything orbits the Earth. Later, we realized the Sun is just one star among billions in a galaxy. In the early 20th century, there was a great debate about whether spiral nebulae were clouds within our Milky Way or separate galaxies far beyond it. Observations by Hubble in the 1920s settled the question. He identified individual stars in Andromeda and measured their distances, proving that Andromeda is a separate galaxy millions of light years away. Our Milky Way was demoted from being the entire universe to being just one galaxy among many. And later still, we realized that our galaxy is just one among billions in the universe. Deep surveys have revealed that the observable universe contains roughly 200 billion galaxies, each containing billions of stars. We're not special. We live in a typical galaxy in a typical part of the universe. Each of these revelations seemed radical at the time, overturning centuries of belief. But they were forced upon us by observations that couldn't be explained any other way. The evidence was too strong to ignore. Could we be at another such turning point? It's possible, though most scientists remain cautious. Extraordinary claims require extraordinary evidence. And while Webb's observations are certainly extraordinary, it's too early to say whether they require overthrowing the Big Bang theory. The observations are still being analyzed. Different research groups are using different techniques and sometimes getting different results. The field needs time to settle and reach a consensus on exactly what Webb is showing us. Only then can we properly assess the implications. But the possibility of a major paradigm shift cannot be dismissed. History has shown that when observations repeatedly contradict a widely accepted theory, the theory eventually has to change. The tension has led to creative proposals. One idea involves what some scientists call superseding. In this scenario, supermassive black holes formed much earlier and more quickly than we thought possible. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive objects collapse under their own gravity. The boundary around a black hole from which nothing can escape is called the event horizon. Once something crosses the event horizon, it's lost forever, falling inexorably toward the infinitely dense central singularity. In the modern universe, stellar mass black holes form when very massive stars die and collapse. When a star more than about 20 times the mass of the Sun runs out of fuel, its core collapses in a fraction of a second. If the core is massive enough, nothing can stop the collapse. Not even the pressure from degenerate neutrons, which is what supports neutron stars, can withstand the gravity. The core collapses to a black hole, and the outer layers fall inward and then rebound in a supernova explosion. These stellar mass black holes typically weigh between 5 and 50 times the mass of the Sun. Supermassive black holes, on the other hand, weigh millions or billions of solar masses and sit at the centers of large galaxies, including our own Milky Way. The black hole at the center of the Milky Way, called Sagittarius A star, weighs about 4 million solar masses. The black hole at the center of the giant elliptical galaxy M87, which was famously imaged by the Event Horizon Telescope in 2019, weighs about 6.5 billion solar masses. These black holes are millions of times more massive than stellar mass black holes. How do they grow so large? The origin of supermassive black holes has long been a mystery. If they grow by accreting gas and merging with other black holes, there's a limit to how fast they can grow. The limit comes from radiation pressure. As gas falls into a black hole, it heats up and emits intense radiation before crossing the event horizon. This radiation pushes against the infalling gas, limiting how much can fall in. The maximum rate is called the Eddington limit, named after Arthur Eddington, who first calculated it. At the Eddington limit, the inward gravitational force is balanced by the outward radiation pressure. Even growing at the Eddington limit, a stellar mass black hole would take billions of years to grow into a supermassive black hole. The growth is exponential, so the black hole's mass increases by a constant factor every few 100 million years. Starting from 10 solar masses, it would take about 1 billion years to reach 1 million solar masses and another 1 billion years to reach 1 billion solar masses. Yet we observe supermassive black holes in galaxies that are less than 1 billion years old, at redshifts of 6 or 7. This has been a puzzle for decades, and Webb has made it even more puzzling by finding massive galaxies with evidence of central black holes at even earlier times, redshifts of 10 or more. The superseding hypothesis proposes that these black holes didn't grow from stellar mass seeds. Instead, they formed directly at much larger masses. If supermassive black holes started at 1 million solar masses or more, they would only need a few 100 million years to grow to the billion solar mass behemoths we observe. These black holes, weighing millions or even billions of times the mass of the Sun, could have acted as seeds around which galaxies rapidly assembled. The intense gravity of a supermassive black hole would have pulled in surrounding gas very efficiently. Gas within a few 100 or 1,000 light years of the black hole would be strongly influenced by its gravity. The energetic feedback from the black hole in the form of jets and winds could have actually promoted star formation in the surrounding gas by compressing it and triggering collapse. When a supermassive black hole accretes gas, it doesn't do so quietly. A small fraction of the infalling material gets ejected in powerful jets moving at nearly the speed of light. These jets plow through the surrounding gas, creating shock waves. The jets can extend for thousands or even millions of light years, far beyond the galaxy itself. The radio galaxies we see in the nearby universe are powered by these jets. The shock waves compress gas, and compressed gas can collapse to form stars. We know that most large galaxies have supermassive black holes at their centers, and there's strong evidence that these black holes and their host galaxies evolved together. Galaxies with more massive black holes tend to have larger stellar bulges. The relationship is remarkably tight. The black hole mass is typically about 1/1000th of the bulge mass. If a galaxy has a bulge containing 10 billion solar masses of stars, its central black hole will weigh about 10 million solar masses. This correlation holds across 5 orders of magnitude in mass, suggesting a fundamental connection. The relationship is so tight that astronomers believe there must be a deep connection between black hole growth and galaxy growth. The black hole affects the galaxy through its feedback, heating gas, and regulating star formation. The galaxy affects the black hole by funneling gas toward it, providing fuel for growth. The two grow together in a dance of mutual influence. If massive black holes form very early, they could have jump-started galaxy formation, helping to explain how galaxies got so big so fast. The black hole's gravity would have assembled the galaxy, while its feedback would have regulated star formation, creating a massive, structured galaxy more quickly than would otherwise be possible. But the superseding hypothesis requires these black holes to form within the first 100 million years after the Big Bang, which is extraordinarily early. The universe at that time was only about 1% of its current age. Most of the structures we're familiar with hadn't formed yet. How would such massive black holes form so quickly? One possibility is that they formed directly from the collapse of enormous clouds of gas, bypassing the usual route of forming from the death of stars. This process is called direct collapse black hole formation, and it's been studied extensively in recent years. Under normal conditions, a gas cloud that starts to collapse will fragment into smaller pieces, each of which becomes a star. Gravity tries to pull the cloud together, but as it contracts, it heats up. If the gas can cool efficiently by radiating away the heat, then different parts of the cloud can collapse at different rates, leading to fragmentation. The cloud breaks up into hundreds or thousands of pieces, each forming a star. This is what happens in star-forming regions today. But if the gas is unusually hot and doesn't contain any metals, it might not fragment. Metals are essential for cooling at certain temperatures. Without them, the gas cools less efficiently in some temperature ranges. If the gas temperature is kept above about 10,000 Kelvin, molecular hydrogen, which is the main coolant in metal-free gas, is dissociated into individual atoms. Atomic hydrogen is a much less efficient coolant. The gas can't radiate energy effectively, so it stays hot. A hot gas cloud doesn't fragment. Instead, the entire cloud might collapse into a single massive object. If the cloud is massive enough, perhaps 100,000 or 1,000,000 times the mass of the Sun, it could collapse directly into a black hole without ever forming a star. The entire mass goes directly to black hole formation, creating a direct collapse black hole. These are called direct collapse black holes, and they're a hot topic in current research. The conditions needed for direct collapse black holes to form are very specific. The gas must be kept hot to prevent fragmentation, which requires intense radiation to flood the region and heat it up. This radiation needs to be in the ultraviolet, with photons energetic enough to dissociate molecular hydrogen, but not so energetic that they ionize the gas completely. The radiation must have an energy between about 11.2 and 13.6 electron volts, corresponding to what's called the Lyman-Werner band. In the early universe, the first stars and quasars might have provided this radiation. When the first massive stars formed, their intense ultraviolet emission could have irradiated nearby regions, creating conditions favorable for direct collapse black holes. The challenge is that the radiation needs to be strong enough to suppress molecular hydrogen, but not so strong that it heats the gas too much or ionizes it. Computer simulations suggest that this Goldilocks zone of conditions might have existed in certain regions of the early universe, allowing some direct collapse black holes to form. These direct collapse black holes would start at masses thousands or tens of thousands of times that of the Sun, giving them a huge head start on growth. From a 100,000 solar mass seed growing at the Eddington limit would reach 1 billion solar masses in less than 1 billion years, easily fast enough to explain the supermassive black holes Webb is finding. Once formed, they could rapidly accrete surrounding gas, growing even larger and influencing the formation of stars around them. The galaxy would build up around the black hole, rather than the black hole forming after the galaxy. The black hole comes first and drives galaxy formation, rather than the galaxy forming first and then growing a black hole at its center. This is an elegant solution that could potentially explain both the early massive galaxies and the early massive black holes. The superseding scenario provides a mechanism for rapid galaxy growth that bypasses the slow hierarchical assembly process. Instead of waiting billions of years for many small galaxies to merge, you start with a massive black hole that rapidly pulls in gas and triggers star formation. Within a few 100 million years, you have a massive galaxy surrounding a massive black hole. But it requires very specific conditions in the early universe that we're not sure actually existed. Direct collapse black holes need the right radiation environment, with intense Lyman-Werner radiation, but not too much ionizing radiation. They need gas that's metal-free, since even a tiny amount of metals would allow the gas to cool and fragment. And they need to form in sufficiently large numbers to account for all the supermassive black holes and massive galaxies we observe. Current estimates suggest that maybe 1 in 1,000 or 1 in 10,000 potential sites would have the right conditions. Is that enough? We don't know yet. Direct collapse black holes are still theoretical, and there's ongoing debate about whether they could have formed in sufficient numbers to account for the observations. Some simulations suggest that direct collapse is rare, occurring only in special circumstances. Others suggest it might be more common if we adjust certain assumptions. The field is actively working to understand whether this mechanism can work and how many direct collapse black holes might have formed. If they're real, they could be the seeds that grew into the supermassive black holes we see today. But proving they existed is challenging. Direct collapse black holes in the early universe would be surrounded by dust and gas, making them difficult to detect directly. We'd need to catch them in the act of forming or find some unique signature that distinguishes them from black holes that form from stars. Another proposal involves modifications to our understanding of dark matter and dark energy. These mysterious components make up roughly 95% of the universe's total mass and energy, yet we know very little about them. They're called dark not because they're black, but because they don't interact with light in any way. They're invisible to all electromagnetic radiation, from radio waves to gamma rays. The only way we know they exist is through their gravitational effects. Dark matter is called dark because it doesn't emit, absorb, or reflect light. We know it exists only because of its gravitational effects. Galaxies rotate faster than they should based on their visible matter, implying there's additional invisible mass holding them together. When astronomers measure the rotation speeds of stars and gas at different distances from a galaxy's center, they find that the speeds don't decrease with distance as they should if only visible matter were present. Instead, the rotation speeds remain roughly constant out to large distances, implying the presence of a massive dark matter halo extending far beyond the visible galaxy. Galaxy clusters are more massive than the sum of their visible galaxies, again implying dark matter. The galaxies in a cluster are moving so fast that they would fly apart unless held together by additional invisible mass. The amount of dark matter needed is about 5 times the amount of visible matter. And gravitational lensing, where massive objects bend the path of light, reveals dark matter distributions that don't match the visible matter. When light from a distant galaxy passes near a massive foreground cluster, the cluster's gravity bends the light, creating distorted images of the background galaxy. By measuring these distortions, astronomers can map the distribution of mass in the cluster, including both visible and dark matter. The result consistently shows that clusters contain far more mass than can be accounted for by stars and gas. The dark matter forms a smooth halo that extends beyond the visible galaxies. Dark matter is invisible and only interacts through gravity, providing the scaffolding on which galaxies form. In the standard model, dark matter is cold, meaning the particles move slowly compared to the speed of light. Cold, dark matter clumps together gradually under gravity, creating a cosmic web of filaments and nodes. The structure of this web is determined by the initial density fluctuations from the Big Bang and by the subsequent growth through gravitational instability. Computer simulations of cold, dark matter structure formation produce a universe that looks remarkably like what we observe, with galaxies clustered along filaments surrounding large voids. Regular matter falls into these dark matter halos and forms galaxies. The gas follows the dark matter, flowing along the filaments and accumulating in the halos. Once in a halo, the gas can cool and collapse to form stars. The dark matter halo provides the gravitational potential, well, that holds everything together. Without dark matter, galaxies as we know them couldn't exist. The visible matter alone doesn't have enough gravity to hold galaxies together. The cold, dark matter model has been very successful at explaining the large-scale structure of the universe, but it makes specific predictions about when and how structures form. And those predictions seem to be violated by Webb's observations of early massive galaxies. What if the behavior of dark matter in the early universe was different from what it is today? What if it clumped together faster, creating deeper gravitational wells that could rapidly pull in gas and trigger intense star formation? Some physicists have suggested that dark matter might not be completely cold as the standard model assumes. Cold dark matter moves slowly and clumps gradually. Its particles have very low velocities, essentially zero from a cosmological perspective. This allows even small-scale structures to form, down to the mass of the Earth or smaller. But if dark matter has even a small amount of warmth or velocity, it could affect how quickly structures form. Warm dark matter particles move faster, perhaps a few % of the speed of light. This free-streaming motion prevents small-scale structures from forming. Structures below a certain mass scale are smoothed out, but it might allow larger structures to form faster. If the dark matter particles are moving and colliding, they could dissipate energy and sink to the centers of halos more quickly, creating denser concentrations. These denser concentrations would have stronger gravity, pulling in gas more efficiently. Warm dark matter would smooth out small-scale structures, but might allow larger structures to form faster. The cutoff scale depends on the mass of the warm dark matter particles. Heavier particles act more like cold dark matter. Lighter particles act more like hot dark matter, which moves at relativistic speeds and prevents all structures from forming until very late. There's a sweet spot in the middle where warm dark matter could potentially explain both the observed large-scale structure and the unexpectedly early formation of massive galaxies. This could potentially help explain why we see large, mature galaxies so early. But current observational constraints on warm dark matter are quite strict. Studies of the Lyman alpha forest, small-scale structure visible in the spectra of distant quasars, place tight limits on how warm dark matter can be. So far, these constraints seem to rule out warm dark matter models that would significantly change structure formation at early times. Alternatively, what if there are interactions between dark matter and normal matter that we haven't detected yet? In the standard model, dark matter is essentially invisible to normal matter except through gravity. Dark matter particles and normal matter particles pass through each other without interacting. But what if there are weak forces between dark matter and normal matter that become important under the extreme conditions of the early universe? Maybe at the high densities and temperatures present shortly after the Big Bang, dark matter and normal matter could exchange energy through some weak interaction. Such interactions could potentially accelerate galaxy formation in ways that our current models don't account for. If dark matter could transfer some of its energy to normal matter, it might help the gas cool and collapse more quickly. Or, if dark matter particles could scatter off normal matter particles, it might affect how the two components mix and settle into structures. These ideas are highly speculative, and there's currently no direct evidence for any interactions between dark matter and normal matter beyond gravity. Experiments searching for dark matter particles have so far come up empty. The LUX, Xenon, and other experiments have looked for signs of dark matter particles colliding with normal matter and have found nothing, placing strict limits on how strongly dark matter can interact. But they're being explored because the observations are so puzzling. When confronted with observations that don't fit existing theories, scientists have to consider all possibilities, even unlikely ones. The history of physics is full of examples where problems were solved by discovering new phenomena or new interactions. Radioactivity, for example, was completely unexpected before it was discovered in the 1890s. Neutrinos were proposed to explain missing energy in nuclear reactions and seemed undetectable for decades before finally being observed. Maybe there's some aspect of dark matter physics that we haven't discovered yet because we haven't looked in the right place or in the right way. There's also the possibility that the so-called dark ages of the universe were not as dark as we thought. Maybe there were more energetic processes happening during that period than our models predict. Perhaps the first stars formed earlier than we assumed, maybe just 50 or 100 million years after the Big Bang instead of 200 or 300 million years. If star formation began earlier, it would give more time for metal enrichment and galaxy growth before Webb observes them at redshifts of 10 or 15. Standard models predict that the first stars formed around 200 million years after the Big Bang, when the first dark matter halos became massive enough to trap gas and allow it to collapse. But this prediction depends on assumptions about how gas cools and collapses, and those assumptions might not be quite right. If there were additional cooling mechanisms we haven't considered, or if the initial conditions were slightly different than we assumed, the first stars could have formed earlier. Even moving star formation back by 100 million years would help somewhat with the timeline problem. If the dark ages were shorter, it gives more time for galaxies to develop before we observe them. Instead of having only 300 million years to form a massive galaxy, you'd have 400 or 500 million years. That's still not enough to fully solve the problem, but it helps. Every extra 100 million years of evolution allows for more star formation, more metal enrichment, more mergers, and more growth. Maybe there were exotic sources of energy or heat in the early universe that we're not aware of, sources that could have affected how gas cooled and collapsed. Some theories propose that decaying dark matter particles could have injected energy into the early universe, heating the gas and affecting star formation. If dark matter particles are not completely stable, but instead decay with a very long half-life, the decay products could be energetic particles that heat the gas. The heating would be strongest in the densest regions where dark matter is most concentrated. This could create a feedback effect where the densest regions, which should form galaxies first, are actually suppressed by dark matter heating. Less dense regions might then form galaxies first. This would change the pattern of structure formation in ways that might help explain the observations. But again, this is highly speculative, and there's no direct evidence for a decaying dark matter. Others suggest that there might have been an early population of very small black holes, called primordial black holes, that formed in the first moments after the Big Bang. Primordial black holes are different from stellar mass black holes because they didn't form from collapsing stars. Instead, they would have formed from density fluctuations in the extremely early universe, in the first fraction of a second after the Big Bang. If a region was dense enough, it could have collapsed directly into a black hole when it entered the cosmic horizon, the distance that light could have traveled since the Big Bang. These primordial black holes could have influenced structure formation by providing gravitational seeds or by injecting energy as they evaporated through Hawking radiation. Stephen Hawking showed in the 1970s that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. The rate of emission is inversely proportional to the black hole's mass. Small black holes evaporate faster than large ones. A black hole with the mass of a mountain would evaporate in about the age of the universe. Smaller black holes would evaporate faster, while larger ones would evaporate much more slowly. If small primordial black holes formed in the early universe and then evaporated, they would have released energy that could have affected the surrounding gas. The radiation from evaporating black holes would heat the gas, potentially triggering or suppressing star formation depending on the details. Alternatively, if the primordial black holes were massive enough not to evaporate, they could have served as seeds around which gas accumulated and galaxies formed. This could provide an alternative to the direct collapse black hole scenario. However, observations place strict limits on how many primordial black holes could exist. Studies of the cosmic microwave background, gravitational lensing, and other phenomena constrain the abundance of primordial black holes at various mass ranges. Current limits suggest that primordial black holes can't make up a large fraction of dark matter, though a small population might exist. These are exotic ideas, but the observations are pushing researchers to consider possibilities that would have seemed far-fetched just a few years ago. When standard models fail to explain new observations, it's time to think outside the box. Science progresses by challenging assumptions and exploring new ideas. Some of these ideas will turn out to be wrong, most of them probably, but one of them might point the way to a breakthrough that resolves the mystery. Then there are the truly radical ideas. Some theorists have proposed that what we're seeing might be evidence of physics beyond the standard model. Perhaps gravity itself behaves differently at cosmic scales or in the extreme conditions of the early universe. Einstein's theory of general relativity has been tested extensively and has passed every test. It correctly predicts the orbit of Mercury, which had been a puzzle in Newtonian gravity. It predicts the bending of light by the sun, confirmed during solar eclipses. It predicts gravitational waves detected by LIGO in 2015. It predicts black holes, which have now been imaged directly. By every measure we have, general relativity is correct. But most of those tests are done in the relatively weak gravity of our solar system or in the modern universe. The strongest gravitational fields we can directly study are around neutron stars and black holes, and even those are limited to the local universe. What if gravity works differently in the extremely dense conditions of the very early universe? What if there are corrections to general relativity that only become important when the density and curvature of space are extremely high? Such corrections could come from quantum gravity, the hypothetical theory that would unify general relativity with quantum mechanics. We don't have a complete theory of quantum gravity yet, but we know it must exist because general relativity and quantum mechanics, our two most fundamental theories, are incompatible at very small scales. Modified theories of gravity, such as modified Newtonian dynamics, or MUND, and various extensions of general relativity, have been proposed to explain other cosmic mysteries like galaxy rotation curves without invoking dark matter. MOND modifies Newton's laws of motion at very low accelerations, which happen to be the conditions at the outer edges of galaxies. Under MOND, stars in the outer parts of galaxies move faster than Newton's laws predict, which matches observations and eliminates the need for dark matter in galaxies. The modification kicks in when the gravitational acceleration falls below a critical value of about 10 to the minus 10 meters per second squared. However, MOND struggles to explain observations on larger scales like galaxy clusters and the cosmic microwave background. Galaxy clusters show strong evidence for dark matter through gravitational lensing and the motion of galaxies. The Bullet cluster, a system of two galaxy clusters that collided, shows a clear separation between the visible matter, which slowed down during the collision, and the dark matter, which passed through unimpeded. This is difficult to explain in MOND but natural in a dark matter model. The cosmic microwave background patterns are also better explained by cold dark matter than by modified gravity. So while MOND works well for individual galaxies, it doesn't seem to be a complete replacement for dark matter. Could these theories or similar modifications to gravity also explain the rapid formation of early galaxies? It's possible, but modifying gravity is a big step, and any such modification needs to be consistent with all the other observations that general relativity explains so well. General relativity predicts black holes, gravitational waves, and the bending of light by gravity, all of which have been observed. The theory also correctly describes the expansion of the universe, the evolution of the cosmos, and the formation of structure through gravitational instability. Any new theory would have to reproduce all of these successes while also explaining the new observations. That's a very high bar to clear. No proposed modification of gravity has yet managed to do so. Another exotic idea is that the early universe underwent a phase transition or some kind of event that temporarily changed the rules of physics. Phase transitions are common in physics. Water undergoing a phase transition from liquid to solid ice is a familiar example. The transition happens suddenly when the temperature drops below 0 degrees Celsius. Above that temperature, water is liquid. Below it, it's solid. The transition involves a fundamental change in the arrangement of molecules. In the early universe, as it cooled, it underwent several phase transitions. The universe transitioned from a quark-gluon plasma to normal matter when it was about a microsecond old. Before that, it was so hot that protons and neutrons couldn't exist. Quarks and gluons, the fundamental constituents, move freely. After the transition, quarks bound together into protons and neutrons. It transitioned from opaque to transparent at recombination about 380,000 years after the Big Bang. Before recombination, the universe was filled with ionized plasma that scattered light. After recombination, neutral atoms formed and light could travel freely. Some theories propose additional phase transitions that could have affected structure formation. For example, if dark matter particles underwent a phase transition in the early universe, changing from one form to another, it could have affected how quickly structures formed. Maybe there was a burst of rapid structure formation triggered by a cosmic phase change, similar to how water suddenly freezes when it reaches a certain temperature. The phase transition could have temporarily changed the properties of dark matter or the strength of gravity, allowing galaxies to form much faster than usual. After this event, things settled back into the slower, more gradual evolution we see in the later universe. The galaxies that formed during this brief window would appear anomalously mature for their age, which is exactly what Webb is seeing. This is highly speculative, and there's no direct evidence for any such phase transition. But it's the kind of outside-the-box thinking that major scientific puzzles sometimes require. History shows that major breakthroughs often come from considering ideas that initially seem crazy. Quantum mechanics seemed absurd when it was first proposed, with its wave-particle duality and uncertainty principle. The idea that atoms were mostly empty space seemed ridiculous in the 1800s. The Big Bang itself was initially dismissed as too weird, with its implication that the universe had a beginning. Sometimes the universe really is stranger than we imagine, and accepting that strangeness is the path to progress. What makes this situation so fascinating is that we're not just tweaking a small detail in our models. We're potentially looking at a fundamental gap in our understanding. The discoveries Webb is making are forcing astronomers to go back to the drawing board and ask deep questions. How do galaxies really form? What determines how fast they grow? What role do black holes play in the process? How does dark matter influence structure formation in the early universe? What were the actual conditions like in the first few 100 million years after the Big Bang? Are there physical processes or phenomena we haven't discovered yet? These aren't small questions, they're fundamental to our understanding of the universe's history and our place within it. The story of these impossible galaxies is still being written. Scientists are working around the clock to make sense of the data, to test new theories, and to plan future observations. Each discovery brings us one step closer to understanding the true nature of the cosmos. And while we don't have all the answers yet, we have something just as valuable. We have the curiosity and the tools to keep searching. We have the drive to push the boundaries of human knowledge, and we have the humility to admit when the universe shows us that we were wrong. The James Webb Space Telescope has given us an incredible gift. It's shown us a universe that refuses to be tamed by our theories or constrained by our expectations. It's revealed cosmic structures that challenge the very foundations of our understanding. And in doing so, it's reminded us why we do science in the first place. Not because we have all the answers, but because we're brave enough to ask the questions. Not because the universe is simple and orderly, but because it's gloriously, magnificently, beautifully complex. The photo that James Webb captured is just the beginning. It's the opening chapter of a new era in astronomy, an era where we can finally see the universe as it truly was in its infancy. And what we're seeing is both humbling and exhilarating. The impossible galaxies are real, the mystery is real, and the adventure to solve it is just beginning. What the James Webb Space Telescope captured when it looked too far into space is nothing less than a revolution in our understanding of the universe. A revolution that challenges everything, changes everything, and invites us all to reimagine the cosmic story from the very beginning. The universe has spoken through the light of these ancient galaxies, and it's telling us that we have so much more to learn, so many more mysteries to unravel, so many more wonders to discover. And honestly, that's the most exciting revelation of all. The journey of cosmic discovery continues, and the best is yet to come. As we stand on the brink of a new understanding, we're reminded that every great scientific revolution began with observations that didn't fit. Galileo's moons of Jupiter, Hubble's expanding universe, the cosmic microwave background, and now Webb's ancient galaxies. Each forced us to expand our thinking, to question our assumptions, and to embrace a more complex and wonderful cosmos than we had imagined. The galaxies Webb found don't just represent a scientific puzzle. They represent something deeper, something that speaks to the human condition itself. For thousands of years, humans have looked up at the stars and wondered about our origins. We've created myths and legends, built philosophical systems, and developed scientific theories, all in pursuit of understanding where we came from and why we're here. These ancient galaxies are part of that answer. They show us the universe in its youth, when the first structures were forming, when the first stars were lighting up the darkness, when the building blocks of everything we see today were being assembled. In a very real sense, looking at these galaxies is like looking at our own family album. The atoms in our bodies, the oxygen we breathe, the carbon in our DNA, all of it was forged in stars that lived and died billions of years ago. Some of those stars might have been part of these early galaxies Webb is observing. The iron in your blood was created in a supernova explosion perhaps 13 billion years ago in one of these ancient galaxies. You are connected to these distant objects in the most fundamental way possible. You are literally made from their remnants. This connection makes the mystery of these galaxies even more profound. Understanding how they formed isn't just an academic exercise, it's understanding our own origins. If galaxies formed faster than we thought, if the early universe was more dynamic and active, then the conditions for life might have emerged earlier too. The heavy elements necessary for planets and life might have been created sooner. The story of life in the universe might be longer and richer than we realized. And as we continue to study these galaxies, as we gather more data and refine our theories, we're not just learning about the past, we're learning about the fundamental nature of reality. We're probing the limits of our physical theories. We're testing whether our understanding of gravity, dark matter, and cosmic evolution is correct. We're exploring whether there are new phenomena, new physics, new aspects of reality that we haven't discovered yet. This is science at its most fundamental and most exciting. The next few years will be crucial. Webb will continue to observe the early universe, gathering more data on these mysterious galaxies. Other telescopes will join the effort, both on the ground and in space. Theorists will work to develop new models and simulations. The field will converge on an explanation, whether it's a refinement of our current models or something more revolutionary. But regardless of where the science leads, one thing is certain. The universe is more amazing than we ever imagined, and our journey to understand it has only just begun. So when you look up at the night sky tonight, remember what Webb has shown us. Remember that the universe has a history, a story that stretches back nearly 14 billion years. Remember that we're part of that story, connected to the most distant galaxies by the atoms we're made of. Remember that there are still mysteries out there waiting to be solved, questions waiting to be answered, wonders waiting to be discovered. And remember that humanity has the tools and the curiosity to keep exploring, to keep questioning, to keep pushing the boundaries of what we know. The photograph that shouldn't exist has changed everything. It's shown us a universe that formed faster, evolved quicker, and became more complex in less time than we thought possible. It's challenged our theories and forced us to reconsider our understanding of cosmic history. But most importantly, it's reminded us that the universe is full of surprises, that nature is more clever than our models, and that the adventure of discovery is far from over. The cosmos is vast, mysterious, and endlessly fascinating, and we're privileged to live in a time when we can explore it, question it, and begin to understand it. That's the real gift that James Webb has given us, not just beautiful images or confounding data, but a renewed sense of wonder at the magnificent universe we inhabit. The universe is waiting for us to understand it, and thanks to Webb, we're one step closer. These galaxies that broke all the rules, that appeared when they shouldn't have, that grew faster than physics allowed, are teaching us the most important lesson of all. Reality is stranger, richer, and more wonderful than anything we could have predicted. And that makes the journey of discovery all the more worthwhile.